Welcome to the STEM Pathways podcast, where we delve into the fascinating world of science, technology, engineering, and math. I'm your host, Rohan Sharma, a passionate explorer of all things STEM. Each episode, we bring to you captivating stories, cutting edge research, and inspiring interviews with experts and enthusiasts who are pushing the boundaries of innovation. Whether you're a student, a professional, or just curious about how the world works, join us as we unlock the mysteries of the universe and explore the endless possibilities of STEM. Let's get started. Today, I'll be interviewing Jim Dakin, who holds a bachelor's in physics from Harvard and a PhD in physics from Princeton. How are you doing today?
Doing great, thank you.
Yeah. So, starting off, I want to ask you what inspired you to major in physics?
Well, that's a, a simple and pretty specific story. First of all, I grew up in a household where my father was a PhD physical chemist, and my mother is an MD, medical doctor, and she often says that I was born knowing physics. I don't know whether that's true or not, but there is certainly a genetic component there. And my mother, in fact, had a sort of an interesting story. She was born in 1911, and she went to well, she was the valedictorian of her high school class in Syracuse, I think. And her favorite subject was chemistry, not physics. But when she got to the University of Wisconsin, she was told there were no jobs for women in chemistry, so she should major in home economics. So she majored in home economics, which was sort of discouraging. And one thing led to another, and she eventually got an MD degree and lived out her life very happily as a general practitioner with her office in the house. So, I had two parents that were very supportive of STEM kinds of education. But there's
Where'd
a
your dad
second
go?
piece. What's that?
Or where'd your dad go?
Oh, he went to the University of Minnesota. His family was very poor. He rode the streetcar to college, and he had two paper routes in the morning, and that's how he paid his tuition. And then was getting a master. He was in a PhD program at Michigan State, which is where I met my mother. And halfway through that, he applied for a scholarship for people from Minnesota to get PhDs at Harvard, and he won the scholarship, so he ended up with getting a PhD at Harvard. But back to but he'd met my mother at Michigan State, where she was doing a dietetics degree and he was doing a physical chemistry degree. But okay, so I was born in 1945, and someplace along the line, about the time I was maybe in seventh grade, the Russians launched Sputnik. And suddenly, the US, there was a great awakening that really impacted my generation, especially of the importance of STEM education, the Russians and so forth. So suddenly, out of the clear blue, as I was entering eighth grade, my high school, very small high school in rural Pennsylvania, offered an accelerated program, an accelerated track in STEM, basically, which allowed me to take, by the time I was a senior in high school, AP biology, AP chemistry, AP calculus, AP physics. That hadn't been available a year before me. So I was really, really prepared for college because of that, because of Sputnik and that accelerated education that happened for my generation in particular. And, and it gets, but I don't know whether you're going to ask about light at some point. Uh, but certainly throughout this STEM education, I was intrigued by optics and light and so forth. And I claim that that all started, my father was very, very nurturing of this STEM education. And when I was an elementary student, he was teaching me photography and teaching me darkroom skills and stuff like that. So I had a hands-on experience with light from a very young age. You want to talk about college, or is that?
Uh, yeah. Um, yeah. Can you talk about what your experience was like then when getting your bachelor's?
Well, okay, so I arrived at Harvard, and to be perfectly honest with you, this was another interesting piece of the story, but very important to your audience here. Uh, I came from a small town in the mountains of Pennsylvania, as I may have said, about 20 miles east of Pittsburgh. It was just starting to be a suburb. And I had it in my mind that I wanted to go to a small liberal arts college in a small college town. And I had two places in mind, Oberlin and Amherst, both of which are very fine colleges. And uh, and I was admitted to both of those. But then a friend of my father's said to him to tell me that if I was really serious about a getting, pursuing a career in science and STEM, I really needed to go to a university that had a strong graduate program. And for that reason, I begrudgingly went to Harvard instead of Oberlin or Amherst. And in the end, it turned out to be the right decision because of the kinds of professors I was exposed to at Harvard.
Oh,
And I,
back then was Harvard still like one of the top institutions?
yeah, I mean, I think a lot about this. I often tell young people where you go. I have a nephew, for instance, who is interested in physics, and I laid out some options for him, and I looked at because of advice that I had received. I looked at which were the PhD programs that had the best rankings, and it looked to me as if he could probably get into the University of Colorado in Boulder, and Boulder had a very, very highly ranked physics department. And so he applied there and he went there and he's having a wonderful experience in Boulder. I mean, it doesn't have to be number one or number two. The part of the reason Harvard gets such a high ranking is because of the overall program, across the board, and the graduate program and the professional schools, law and medicine and business and whatnot. But if you narrow it down to what you're interested in, you don't necessarily have to go to a Harvard. Go to a place. Now, when I got to Harvard, it turns out that because of the Sputnik and the STEM thing that I just mentioned, a great many of my classmates also wanted to major in STEM disciplines. But by our sophomore year, at least half of them, maybe more than half, had dropped out into other fields. And I was one of the lower percentage, less than half in physics that stuck it out. Um, I, I, uh, I well, I did because of the accelerated program in my high school. I did very well in the freshman physics course. I did so well by myself get money by grading the the homework assignments of freshmen when I was in my advisor, Nobel laureate. He was the guy who developed something called the hydrogen maser, which is the world's most accurate clock. I may get this wrong, but I think it's significant. It's accurate to something like 13 significant digits, accurate, stable, whatnot. And the hydrogen maser in those satellites going around the Earth is what makes GPS possible. Because by comparing your cell phone when you're sitting in your desk right there, is getting signals from these satellites, and by getting three or more signals and comparing the arrival times of those signals, it's able to tell within I don't know, 10 or 20 feet where you are on the earth because of my thesis advisor or because of my undergraduate advisor. It was exciting to meet people like those, like him. I, I, I had another experience at Harvard. In other fields in Harvard, in undergraduate, in things like history or English or whatever, there was a thing called tutorial, especially your junior and senior year, where instead of a class, you meet in a much smaller group with a tutor, and by senior year, you write a thesis working with a tutor. And I went to my physics department and I said, why can't we have something like that in physics? And they said, go see this guy, Gerald Holton. So I went to see Gerald Holton, and he was a physics professor. He was very interested in the history of physics. And that sort of comes back later in this story. Uh, when Einstein died, they pulled Holton out of Harvard and sent him to the Institute of Advanced Physics and gave him the job of organizing Einstein's papers. I mean, this guy was very well connected, and he helped me organize at Harvard there are these things called houses. They're sort of like dormitories, but they have dining and common rooms and things like that associated with them. But he helped me to organize a thing where once every couple of weeks, a professor from some STEM field would come and have dinner with us, and he would give us a paper to read beforehand, and we'd talk about the paper. And in fact, Holton told us to read a famous paper called Einstein, Podolsky, and Rosen, which is, I'll never forget that discussion. Einstein was a person who didn't fully accept the idea of quantum mechanics. And in that paper, he presented the theoretical objection quantum mechanics, the inaccurate objection. But I had a great experience. But it all comes back to this notion of it's not so important what you do is where you go is what you do when you get there. I think at most top-ranked universities, I think you can get a great education if you pursue stuff that if you hang out with people that bring out the best in you and you pursue activities that develop you and so forth. I think that's one of the great truths. And, people get this idea in their head that they have to go to some place or another because an uncle went there or because they heard it's the best or whatever. And that's just baloney. My nephew is having a great experience at University of Colorado Boulder, for instance. He's helping out on experiments during the term year and getting summer jobs with them and so forth, and learning all sorts of stuff about lasers in particular.
Next, I wanted to ask you what made you want to do a PhD.
Well, I mean, I had it in my head that I wanted to have an academic career. I wanted to be a professor. And you can't be a professor without a PhD. So that's kind of what drew that. That's kind of a simple answer.
Oh, and then while you're at Princeton, what was your PhD about?
Well, I was very, very much excited by elementary particle physics at the time. Electrons and protons and mesons and neutrinos and all that kind of stuff. And I quickly figured out that I didn't have the mathematical insights to be a theoretical physicist. I had to be an experimental physicist. And that was the hot area at the time. I'll never, you must have heard of quarks. Do you know about quarks?
Yeah.
Yeah, basically, protons and neutrons are made out of quarks. It was once thought that there were three kinds of quarks: the up, the down, and the strange. But Okay, so at that, I'll never forget going to an American Physical Society meeting in New York. I mean, there was a lot of skepticism about quarks. There were these guys, maybe one of them was Gell-Mann, that proposed the idea of quarks. And no one had ever seen one of these experimentally, but they were proposed. And I went to an American Physical Society meeting in Washington for the first time and heard this guy, Richard Feynman, give a talk. And this wasn't his field. He had invented something called quantum electrodynamics, um, which is it's valid to this day. And but that wasn't what he talked about at this talk. He talked about the overwhelming evidence that there were these quarks that just pointed in that direction. And I got myself really excited about elementary particle physics and did a PhD thesis working with a team experimentation in that area. And then that led to my getting a postdoc opportunity at Stanford in the same field. At that point, Stanford had the best electron accelerator in the world, the highest energy. And they were doing some experiments there that were basically probing the inner structure of protons and neutrons and things and showing increasingly credible evidence that these quarks, in fact, existed. In fact, I had the good fortune at Stanford of working on two different experiments, each of which, I mean, I was a postdoc at this time, but in each of these experiments, the team leader won a Nobel Prize. And that was just just blew my mind. I mean, the stuff we were finding was like cutting edge, state of the art. It was exciting. Um, and I had 2.5 years there. It was a great 2.5 years, and that led to my getting a. I'm probably getting ahead of you here, but that led to my getting a job at the University of Massachusetts as an assistant professor because of this pedigree that I had from Princeton and Stanford and so forth.
Oh, what was your?
However,
Sorry,
excuse
you
me.
go. You or you can go. You go.
But the next chapter there was I was just at UMass for 2 years. I had a tenure track position, which up until that point in my life I thought was the holy grail. Uh, and But we had this thing called the first energy crisis right back around then. Let's call it 1973, 1974. The Arab oil gas pump skyrocketed. There were lines at the pump. And everyone was suddenly, for the first time, worried about energy. We were still worried about energy. We were really worried about it then. And I was actually becoming a little bit disillusioned with elementary particle physics, not because it wasn't cool, but because I couldn't see any practical benefit to it that was, benefiting mankind. Certainly, it wasn't solving the energy crisis. Um, so I decided I really wanted to do something different with my life. I wanted to do something that had practical impact. And while I was at Princeton, I actually had applied for a job at the GE General Electric R&D Center in Schenectady. And at that time, they actually didn't have any jobs, but I remember the guy who interviewed me, and I got back in touch with him. Bingo, I got a job offer from the R&D Center, working on a project that I knew absolutely nothing about, zero. It is a problem that involved gas turbines and heat transfer. I had never taken the engineering courses that gave me any kind of background in that. Gas turbines, heat transfer, material science. So, I briefly had a deer in the headlights kind of moment, And but then I started digging in and quickly learning as much as I possibly could about the particular problem I was working on, which was a very practical problem that was going to increase the efficiency of gas turbines and therefore make electric generation more efficient. And I quickly became the world expert in this problem I was working on. And of course, that's one the point of view of these interviews you're doing is you have to in your career the world's always changing and new opportunities are arising. Years later, I so at age 30, I what I still call my midlife crisis. I wanted to get out of academic physics and high energy physics. I wanted to get into something practical at GE. And 37, do you the numbers, 37 years with GE, doing all sorts of different things. But a couple of years ago, I published a letter to the editor in Physics Today about that decision at age 30. And I got a lot of very interesting responses to that letter. It was from a poor soul that one of the universities who had taken a postdoc in the kind of general field that I had, but too long and wasn't learning new skills. And we spent 10 years or something working on a project that wasn't teaching him new skills, and he felt trapped. It's pursuant to your interest in these interviews, it's so important in career to continue advancing yourself, moving from where you are to someplace else that teaches you new skills and builds upon what you already know. And you develop self-confidence by doing that. And I've been through that many times in my career at GE and since.
Yeah. So, when you're at GE, what was the most interesting thing that you think you worked on?
What was the most interesting thing that I worked on? I worked on all sorts of interesting things. I I had a great time at GE. I worked on that problem that involved gas turbines for a couple of years, and then I got recruited to be something called a liaison scientist. Uh, and my job was to visit GE businesses around the world, literally, and learn about what they were doing and how the R&D center work where I was at was benefiting them or could benefit them if we changed directions. I visited I visited Italy, I visited England, I visited Canada, I visited Switzerland, I visited Brazil, Mexico, you name it. I was all over the place, and that was absolutely fascinating. Um, I'm not sure it benefited GE a lot. It taught me a lot about the GE businesses and the business equation and so forth, and the fact that all of these businesses were constantly having to improve their products in order to stay competitive. And I learned a whole lot about the whole product line. And then a after about let's say 3 years of that, I was transitioned into a job in into electric lighting at the R&D center. And in particular, in developing new light sources, they had traditionally done a great deal of what they called matrix testing. How and the way multidimensional grid of all the different design parameters, like the length, the diameter, the pressure, the gas composition, the filament diameter, whatever, and you build all permutations and combinations and test them, and then do a mathematical model and figure out which is the sweet spot in that whole design space to make the product. And the question was there a smarter way to do that? So I was given the job of developing predictive models, first principles models that were based on first principles, um, that could predict the performance of a category of light bulbs, the so-called discharge lamps, that involved electricity going through gas. These are common. They were first used in streetlights, fluorescent lamps, more recently in high bay, and so forth. In any case, I did. In fact, I became the best person in the world at doing these models. I got invited to conferences and things. But and then in the middle of all this, I moved from the R&D center in Schenectady to the headquarters of the lighting business in Cleveland. Build on it. Anyway, one thing led to another, and a certain competitor had come out with a product, and I was able to instantly understand why that product was as good as it was, and why we GE had to have that product. And I quickly got responsibility for organizing a team and designing such a product and getting it into production. And it was the insight from the models that enabled me to do that. So it was suddenly big time into manufacturing and stuff like that. We had in this product line that I got going, we had operations in the US, in Canada, in Mexico, in Hungary, in Japan, in China. All of this stuff was coordinated together, making a final product, and it required very little investment, which was a good thing because it drew on capabilities that we had in all those places. But again, I was learning new stuff I didn't. I mean, I was so lucky at GE to always have so many people around me that knew stuff that I didn't know that I was able to learn from. From that first experience in GE, I was sorely lacking in material science, something that mechanical engineers especially get a heavy dose of. I think some physicists do, depending on the work that they're doing, probably more now so than earlier. But yeah, material science is so important. And I didn't learn any of that in my undergraduate courses, zero. But I was constantly having to learn it along the way. And I was constantly fortunate to have people around me that I could learn from. It was just a wonderful environment. I'm sure they were learning stuff from me too. It's no man is an island. You've heard that phrase, I'm sure.
Yeah. Now can we move on to what your consulting was like?
Well, okay, so toward the end of my career, for maybe the last 5 or 10 years, I had a so-called chief engineer role. And my role was to basically review every product change that we made around the world and make sure we weren't going to screw up. And there were so many ways to screw up. Well, for instance, the product could be unsafe. The product could not comply with government regulations. The product could be not manufacturable. The product might be one that nobody wants. So we had a very sophisticated checklist that we had. And I would go down the work, and often a young person, not much older than you, would get responsibility for a particular new product and didn't know how much trouble he could get into. We had some spectacular examples of that. But I would do a review that would last a couple hours, and the people knew what I was going to ask, and we would go down the list and so forth. And sometimes they would get a red, which means you have to stop the project, period. Sometimes you get a yellow, which means you're on a good path, but you got to do some more work before going to the next step, or you get a green, which means you go to the next step. Well, anyway, as a result of that, I learned a lot more about the whole range of GE products in that role. And one of the things I learned about was LEDs, which were just starting to take off during that time period. They were replacing all of the traditional technologies. Learned a little bit about them. And okay, so then I retired and I sort of put out my shingle and tried to look for clients. And it turns out mostly clients found me drawing on things that they knew that I knew about. There was one category of clients that wanted to draw on my experience with discharge lamps, like the one that I talked about getting into production. But there was one in particular that came a product into production that had something called UL approval, Underwriter's Lab. You have to, for something to be electrically safe in the US, it has to have underwriter approval. So everyone gets Underwriter's Lab approval. One of the criteria is if you're going to change the product, you better get Underwriter's Lab to approve the change. Well, anyway, this company had put a product into production that was made in China and by a Chinese supplier. And then they asked to have a lower cost version of the product. So the Chinese supplier made lots of changes and they started selling this thing without realizing that they had completely invalidated their UL approval. So because of the experience of my last job at GE, I was able to help them understand the kind of discipline you have to do to avoid that situation. We had a very, very, very good process at GE for avoiding screw-ups. But okay, so I just have a whole bunch of different things. The most interesting thing was I was approached by a company called Seoul Semiconductor. They were based in Korea, in Seoul, Korea. And they were not the biggest, but almost the biggest supplier of LED chips for the new LED light bulbs. And they needed someone to represent them in standard bodies like UL, for instance. Just keep them to track of all the changes that were happening in the standards, international standards pertaining to light bulbs. And these are things that are all over the world. There's some there's some so-called IEC standards. There are national standards, there are European standards, there are country-specific standards, and even state-specific standards. They needed an organized way to keep track. And of course, these standards were all changing because the whole landscape was changing from traditional forms of lighting, like incandescent light bulbs, to the new forms like LEDs. Well, anyway, because of my background, I was able to quickly come up to speed in the world of standards and go to standards meetings around the world. I even went to one in Indonesia once. I went to standards meeting in Europe and all around the US. So for several years, that was kind of a half-time or quarter-time job for me at a very good rate, I might add. Significant cost savings. There were all sorts of little things that came up. But as about the time that COVID came along, that business was tapering off for me, and I sort of lost interest in it. And furthermore, because my background was primarily with the traditional technologies, not with the LEDs, my background was becoming less and less relevant. Make sense?
Yeah. Uh, All right, can you tell us a bit about what your book's about?
Uh, yeah, actually two books, or maybe three books. Uh, about 5 years ago, I wrote a personal memoir, which has never been published. And it's the title of it is Life and Light. And this has never been published. It was just from my family, basically. Uh, and maybe a couple hundred, and some friends asked for copies, but never been sold, for instance. But I use light as an organizing theme in this because, as I told you earlier, it went all the way back to my childhood. Uh, when I was in, oh boy, where is it here? When I was in middle school, my father, I've talked about him being an influence, had given me a book called The Universe of Light that was written about 100 years ago by a guy named Bragg, who actually is associated with X-ray diffraction and stuff. But it talked about the huge okay, keep in mind, I'm like a seventh grader. I'm younger than you are now. My father gives me this book and I read it. And I still remember it. Uh, okay, so I one thing I came to understand is that light is a very broad topic. It shows up everywhere. It shows up in architecture. It shows up in biology. It shows up in ancient philosophy. It shows up in religion. It shows up in medicine. It shows up in physics and in chemistry. You name it. Shows up in astrophysics. And it because of all this stuff, it became increasingly obvious to me that the whole story couldn't be found in one place. So I wrote this book here, published this maybe 3 years ago. It's formatted as a textbook to be used in an interdisciplinary college level course that puts the whole story in one place. Okay. And that led to my teaching a course about a year ago at Appalachian State in Boone, North Carolina. The name of the course was Light and Color. And I basically followed this textbook in the course. It was an interdisciplinary honors course. In fact, there was only one STEM student in the course. He was a math student, not a physical science kind of student. And as I was doing this, I came to understand that for the non-STEM students, which most of mine were, every time they saw an equation, they would get a deer in the headlights kind of look in their eyes. It would spook them. So I started thinking to myself, actually 3 years ago, how do I tell this story without equations? And that led to this book, which was just published this month, Shining Art on Light. And this book does not have a single equation or a single graph in it. What it does is it has art from museums. And the whole story of light, from the Big Bang to the present, is told through art from museums. There's a picture in here. We had an eclipse recently. There's a picture in here. Let me try to find it for you. This is a picture that's at the Getty Museum in Los Angeles, and it's about an eclipse that occurred in France several hundred years ago, before people were able to predict eclipses. And if you were a person that worshiped the sun, can you imagine how terrifying it would be if the sun went away? Just think about it. there's the sun. It's giving you heat. It's helping you grow your crops. And you're out in the field one day, and all of a sudden the sun goes away. Think how spooky that would be. I mean, nowadays, when we have an eclipse, we know it's coming. It's going to last a couple of minutes. It's going to be a tourist attraction. Everyone's going to be happy. Anyway, I got this thing is just full of pictures like that from museums that tell the broad story of life, the natural phenomena, the human inventions, and a little bit of the underlying science, all using art. Another one of my favorite examples here is waves or particles. Okay, so you're in a introductory physics course or something, and you say to the class, light, some people thought light was waves. And people think, what the hell's a wave? Is it something in your hair? Is it waving to someone? Is it what you do at a football stadium when there's some downtime and you want to make everyone happy? So in here, I've got a picture of some waves on the ocean. That's what we mean when we say light was like waves. And that kind of thing, I mean, that very simple understanding gets glossed over when the story, when people try to tell the story to non-STEM students in particular, without the use of equations. What is a wave? Here's my wife. You have to go away, Carl. I'm being interviewed.
I want a $10 bill.
You'll have to edit this out of the interview.
I want to give her, thank you. Wedding gift with the 220s.
Here I am.
Hmm.
Where were we?
Yeah.
And by the way, the thing I'm doing mostly right now is learning how to be a real author and market this book.
How are you going about that?
Well, it's a learning experience. First of all, you spread the word on social media. You get some friends who might be interested to take copies and write reviews of it. You sign up for all the events you can possibly find. I'm signed up for the Chicago for the Printers Row Book Fair in Chicago in September. I'm signed up for a huge book fair in Frankfurt in October, where the book will be displayed and there'll be in catalogs and people can click and whatnot. You place ads. I'm placing an ad in the Physics Teacher, which is there's a thing called the American Association of Physics Teachers, of which I'm now a member, and they have a monthly periodical for physics teachers, people that teach physics to high school students and entry-level college students, mostly non-STEM. And it struck me that this book would be ideal for that audience. So I placed an ad in the Physics Teacher. And I'm getting a book review posted in the Physics Teacher from a friend. But I'm learning as fast as I can how to market a book, which is something I have no skills in going into this. I have a friend in Cleveland here whose daughter is part of the book scene in New York, and they introduced me to her, and she gave me kind of a crash course about 6 weeks ago in the kinds of stuff I have to do. I'm now a member of something called the Authors Guild, and they have a lot of material on do's and don'ts and so forth of promoting books.
But yeah, thank you for meeting with me.
Well, it's been a pleasure. I hope someone finds this interesting and helpful. The main takeaway is be prepared to learn new stuff all the time and see where the world is going and try to go there with them. If you try to stay static, the world's going to pass you by. You have to keep learning new stuff. Thank you.
Thanks.